Welcome. In this lecture, we shall look at some practice problems on flitched or composite beams. The practice problem 11 is stated as a flitched beam consists of steel and timber as shown in the figure. Determine the moment of resistance of the beam. Take bending stress in steel as 100 megapascals and bending stress in wood as 5 megapascals. All dimensions are in millimeters in the figure. The given figure is drawn for reference here along with dimensions. You may pause the video briefly at this stage, solve for the unknown parameter, and resume watching when the solution is ready for checking your answer. The solution to practice problem 11 is provided here for reference. The unknown moment of resistance is given by the summation of the moment of resistances for wood and steel and is calculated as 10 in kilonewton meter units. Now let's proceed to practice problem 12, which is stated as a composite beam having the cross-sectional dimensions as shown in figure is subjected to a bending moment of 40 kilonewton meter. Materials are fastened so that the beam acts as a single unit. Determine the maximum bending stresses in each material. Dimensions in the figure are in millimeters. Take Young's modulus in steel equal to 2 times 10 to the power of 5 megapascals. Young's modulus in aluminium equal to 0.67 times 10 to the power of 5 megapascals, and Young's modulus in cast iron equal to 1 times 10 to the power of 5 megapascals. The given beam is drawn here for reference. You may again pause the video at this stage and resume when the solution is ready for checking purposes. The solution to practice problem 12 is provided here, where the composite section is first converted to an equivalent steel section for convenience and ease of calculations. The corresponding modular ratio is considered for minimizing the width dimensions of both the cast iron as well as the aluminium part of the beam. For cast iron, the modular ratio is found to be 2, and for aluminium, it is found to be approximately 3. We then find the vertical centroid location from the base of the equivalent steel section as 162.5 millimeters, which is coincidentally found to be at the center of the steel part of the composite beam. From this information, we proceed to calculate the area moment of inertia about the centroidal or neutral axis using parallel or a transfer axis theorem, and is found as 7.537 times 10 to the power of 7 in millimeter to the power of 4 units. Now, the bending stress distribution diagram is drawn for the equivalent steel section, wherein the maximum stress is found to be 72.97 megapascals. For the bottom layer, it is calculated as 86.24 megapascals. For steel, the maximum stress is found from simple interpolation as 33.17 megapascals. We still need to find the maximum stresses in the cast iron and aluminum materials based on the knowledge of equivalent steel material at the corresponding levels. Because the strains at the interface of different materials are the same, hence we calculate the stresses in the cast iron and aluminum materials as 36.49 megapascals and 28.75 megapascals respectively based on Hooke's law. Now we proceed to the last practice problem here. A timber beam 300 millimeters wide and 300 millimeters deep is reinforced by two steel plates 300 millimeters wide and 6.25 millimeters thick attached at the top and bottom of the joint. The composite beam is simply supported at its ends and carries a uniformly distributed load of 25 kN per meter over an effective span of 6 meters. Find the maximum bending stress in steel and timber at the midspan. Take Young's modulus for steel as 200 kilonewton per millimeter square and for wood as 10 kilonewtons per millimeter square. You may again pause the video here briefly and resume watching when the solution is ready. The solution to practice problem 13 is given here for reference. The modular ratio is first found out to be equal to 20. The composite beam is drawn and then converted to an equivalent steel section for ease of calculations and convenience. The value of maximum bending moment is calculated as 112.5 in kilonewton meter units based on the nature of loading. The area moment of inertia for the equivalent steel section is then found out approximately as 12.16 times 10 to the power of 7 in millimeter to the power of 4 units. The maximum bending stress in steel is calculated from the flexure formula as 144.45 megapascals. By interpolation, the stress at the level of steel-wood interface is found to be 138.67 megapascals. Now, because the strains in the two materials at the common interface are the same, and from the knowledge of Hooke's law and modular ratio, we find the maximum bending stress induced in wood as 6.93 megapascals. The actual bending stress distribution diagram in the two materials is also drawn for reference. We hereby complete the chapter on bending stress in beams. In the next lecture, we begin with a new chapter, namely shear stress in beams.